Before we jump into this episode, I want to take a minute to talk about a comment from episode 2. This comment by M. Hussein Mahmoudi asking why we don't just use the pragma once directive rather than the verbose include guards I showed. I knew about pragma once, but I hadn't looked into it enough. But now I have, albeit briefly. Pragma once is non-standard, but it's so widely supported that it shouldn't cause any issues for us to use it, and it has some marginal benefits. The include guard method has a chance of naming collisions. It may have slower compile times, and it's generally more annoying to type. I think that's the main downside. Either way is fine. I'll be using pragma once going forward. Thanks for the comment, Mr. Mahmoudi. One more thing before I get started. I made a mistake in the last episode. The error exit macro doesn't call exit, so let's fix that quickly. In order to gain more control of what we're rendering to the screen, we need to load some shader files and give them to our GPU via OpenGL. As such, the first thing we need to do is write a file loading function. We'll create another module directory inside Engine called IO. This module will just contain io.c and io.h. First up, in io.h, we'll define a custom file type and two functions, iofileRead and iofileWrite. IofileRead returns the custom file type we just made and takes in one argument, path to the file. That path is relative to your executable. IofileWrite returns an int and takes in three arguments. Buffer is a void pointer to the memory we want to copy to a file. Size is just the size in bytes of the buffer. Path is where we want to save it, again relative to our executable. Now copy the function prototypes into io.c. We need a few includes here. We'll also define a few local macros. The first one will become clear as to why shortly. The other two are error messages that we'll repeat in the code below. We'll initialize the file and explicitly set the isValid flag to false for clarity. Next up, we'll use the fopen function and grab the file pointer. Fopen takes two arguments. The first is the path and the second is one or more options for what permissions we want. In our case, we just want to read, but we want to use binary format, so we'll put a lowercase rb here. If the file pointer is null, we'll just use our error return macro here, and the outer scope can figure out what to do. The reason we don't just exit here like we do in other places is because there may be some circumstances where you want the user to be able to open a file but not close the program if something goes wrong. For example, loading a save file, but the save file is missing. Or if they typed in a path and made a typo, it'd be pretty annoying if the game just exits in that. This file reading solution is a bit more complex than the ones that you'll find when you search for how to do this. It's adapted from the only solution I could find that doesn't use the fseek function. And the reason we don't want to use the fseek function is because it can cause undefined behavior when dealing with binary files. You can check out the link for specific details. We'll need two character pointers, data to hold the data we read from the file, and temp. We'll use used to store how many bytes we've read so far. Size for the next size we're going to allocate. N will hold how many bytes we just read on each iteration. We're going to be using a while loop here with a value of true and break out manually. We'll check if the size of our buffer is too small, and if it is, we'll return that the file is too large. It's actually an overflow check. Let's write out the rest of the function and then we'll run through how it works. First, we open the file for reading in binary format using fopen. The next, we'll allocate another chunk's worth of memory for the data buffer. Reading data from the file using fread returns us the amount of bytes read. If it's 0, then we reach the end of the file, so we break out. Otherwise, we add the amount of bytes read to used and go again from the top. Following that process until the file is read, then we'll check for errors again and resize the data buffer to the correct size. Add a null terminator to the end. For now, we'll just leave iofileWrite as an empty function and come back to it when we implement the configuration module. Now that we can read files into our program, we can start using shaders. Open up render_internal.h, and inside the internal state struct, we want three new fields. We want two U32s. The first one is shader default, the second one is texture color. And we want a matrix, a 4x4 matrix, for our projection. We'll also define a few functions while we're here. Render shader create, used to link our shaders via OpenGL. Render init shaders, another init function that will just initialize our shaders. For now it's just one shader, but we'll have a few later. Render init color texture. We'll create a texture that lets us easily tint what we're drawing to the screen instead of it being white. Copy the render init function prototypes into render init.c and we'll fill those out shortly. First, we'll create a file, render_util.c, inside the render directory, and we'll copy the render shader create function prototype into it. We need to include a bunch of headers here, then head into the function body. This function will load the vertex and fragment shaders into buffers, then compile and link them and give us an ID we can refer to. Briefly, and without going into too much detail, a vertex shader takes in, unsurprisingly, vertices of a 3D object. Everything in OpenGL is 3D, and allows you to do some math with them to determine where they'll be drawn on the screen. The fragment shader then calculates the color of each pixel to be drawn. I recommend checking out learnopengl.com if you want to better understand the OpenGL graphics pipeline. First, we'll need a couple of variables, success and log. These will just be empty for now. Then we'll load our vertex shader using the API we just created. If the file is not valid, we'll error and exit. Next, we'll create an ID for our vertex shader. Then we'll give the source to OpenGL and attempt to compile it. We'll use the glGetShaderIV function, check for the compilation status. If there's any kind of problem, error exit. Now we do exactly the same thing for our fragment shader. If all goes well, we can then create an ID for our final link shader program. Then we'll attach our vertex and fragment shaders, link the program, and check for errors again. Lastly, we'll free the file data and return the compiled and linked shader ID. Now before we can use this function, we need to actually write some shader programs. Project root directory, not in source. Create a directory called shaders, and inside that directory, create two files, default.vert and default.frag. These will be our default shaders. Let's first fill in default.vert. First line of any shader program denotes the version and profile. We chose OpenGL 3.3 and the core profile. Note that we use 330 rather than 3.3. Next up, we'll put in our attributes. In the last episode, we created our quad and told OpenGL that it has two attributes, the position, XYZ, and the UV coordinates. Now we can access these inside the shader. Next up, we'll define an output to pass to the fragment shader. We want to pass the UV so that we can correctly map the texture onto the quad, since the fragment shader handles the coloring of each pixel. Uniforms are values we can pass in every frame and allow us to do things like move objects around or change their color, etc. The projection matrix can be thought of like a camera. In our case, we have an arcade-style game with a fixed camera, so this value is set up once and not changed. The model matrix is how the object we're rendering can be transformed, scaled, and rotated, etc. There's usually a third matrix called the view matrix that handles the position and orientation of the camera. But since we aren't moving the camera, we don't use that. Shaders have a main function, much like a C program, but they return void. Here we'll assign our out UVs and a special value called gl_position. That is the transform position of our vertices. Now save that and open up the fragment shader. Same as before, we'll declare the version. Next, we'll declare an out value, frag_color. Take in the UVs that we sent out from the vertex shader, then set up two uniforms. First is color. We can change the color of things with that. Then texture ID to specify what texture to use. At the moment, we only have one, but in the future, we'll be using a few. Then we blend together the texture and the color by multiplying them together. We pass the UVs to the texture function so it knows which way to draw the texture. And that's it for the shaders. Now we just need to write the init functions and initialize everything. So back in render_init.c, we'll implement the _init functions, starting with render init shaders. We can just call the function we wrote to create a shader and pass in the paths of the vertex and fragment shaders. Then we'll set up our projection matrix. We're using a flat view, which is called orthographic. Now we'll use the program we just created and send it to the projection uniform. That's it. Now let's move on to the color texture init function. First, we'll generate a texture ID, then we'll bind to it. Then we'll use an OpenGL function to write directly into the texture a single white pixel. This texture will be used for drawing solid colored objects. We'll unbind the texture just as a precaution. Okay, now that's done, we can go to render.c. In render init, call the init functions we just created, passing in the required pointers. Move down to render quad. We need to use our shader program and transform the quad. We'll create a model, then reset it to an identity matrix. You can think of that as an expected default transformation. Next, we'll move the quad using translate, then scale it using scale aniso. Then we'll send the model and color data to the shader using the uniforms. Lastly, we'll bind the texture we created and remove the polygon mode call. Now let's head over to main.c. We'll change the color of our quad to green just to test that the color is working. And finally, we'll update the build script. Just adding the new files and splitting the files variable into modules to make it a bit easier to read. Now when we compile and run the program, we should see that our quad is a 50 by 50 green square in the center of the screen.